In this video, we will look at series and parallel connection of elements. We begin with series connection of resistors. We show two circuits. Each circuit is broken up into two parts. There's a rectangular box called the part of circuit, which has two terminals A and D coming out of them for both circuits. The rectangular boxes are identical for both circuits, and we are not interested in what is happening inside these boxes. We are more interested in what is happening outside the box and what is connected at the terminals A and D. Both circuits have the same voltage V1 and current I1 at its terminals. The circuit on the left has three resistors, R1, R2, and R3, that are connected in series because they have the same current I1 flowing through all of them. The circuit on the right has a single resistor, Req, connected between the terminals A and D, and also has the same current I1 flowing through it. What we are interested in finding out is if there is a relationship between the three resistors in the left-hand side circuit and the single resistor Req in the right-hand side circuit. To show the relationship between the two sets of resistors, we will write a KVL equation for both circuits. For the left-hand side, we will write a KVL for the loop A, B, C, D, A. And on the right-hand side, it will simply write a KVL for ADA. Following the passive sign convention, the polarity of the voltages for different resistors is shown. On the left-hand side, as we move from node A to B, we have a voltage drop of I1 R1, another voltage drop of I1 R2 as we move from B to C, and another voltage drop I1 R3. And then we have a voltage rise as we move from D to A of V1, which we will write on the right-hand side, and the voltage drops must be equal to the voltage rises. Similarly, on the circuit on the left, we will have a voltage drop of I1 Req, which must be equal to a voltage rise of V1 in the loop ADA. Since the two voltages V1 must be equal, we can write down that I1 multiplied by R1 plus R2 plus R3 from the left-hand side must be equal to I1 Req from the right-hand side. We can cancel out I1 throughout the equation, and we will be left with that Req is equal to R1 plus R2 plus R3. What this tells us is that if we have resistors in series, then we can replace them by a single resistor, Req, which will be the sum of all the resistors in series, and the two circuits will have identical voltages and currents. What this means is that if we have more than three resistors in series, then the equivalent resistance Req will be the sum of all of these resistors, and if we have n resistors in series, then it will be the sum of all n resistors. Next, we will consider the series connection of voltage sources. Once again, we show two circuits. The circuit on left has three voltage sources connected in series, and the circuit on right has a single equivalent voltage source, E equivalent. For simplicity, we are not showing the rectangular box which is connected to these voltage sources, and we are interested in finding the value of the equivalent voltage source in the right-hand side circuit. For the circuit on the left, as we move from node D to C to B, finally end up at A, we will have a voltage rise of E3, which we will write with a positive sign as we move from D to C. Then we will have a voltage drop of E2, which we will show with a negative sign as we move from C to B. And finally, another voltage rise of E1 as we move from B to A. This must be equal to the same voltage as we move from D to A on the right-hand side circuit, which is a voltage rise of E equivalent, and will be given with a positive sign. And this is the relationship between the circuit on the left and on the right. If we have more than three voltage sources connected in series, then we will simply add up all the voltage sources carefully, making sure that we are adding up the voltage sources with the correct sign depending on how they are connected. Finally, we consider the series connection of current sources. We show three current sources connected in series. If we write the KCL at node B, then we have currents J1 and J2 leaving node B such that J1 plus J2 must be equal to 0, which implies that J1 is equal to minus J2. What this means is that the currents J1 and J2 cannot be arbitrary, and must have a very definite relationship between them to satisfy KCL at node B. Similarly, for node C, we have both currents J2 and J3 entering such that J2 plus J3 must be equal to 0, and as before, J2 must be equal to minus J3. What this tells us is that if two current sources are connected in series, then they must be pointing in the same direction and have the same current value. If they have different current values, then it is not possible to connect current sources in series. From the two KCL equations at nodes B and C, we can derive a relationship between J1 and J3, and we will find that they are equal. What this tells us is that if we are to connect two current sources in series, then they must have the same value and have current flowing in the same direction. Next, we will look at the parallel connection of elements. We show two circuits, one on the left and one on the right. Both circuits are broken up into two parts. There's a rectangular box called part of circuit, which is identical for both circuits. And this part has two terminals A and D coming out of it. The voltage V1 at terminals A and D is the same for both circuits, as well as the current flowing in and out of terminals A and D is identical for both circuits. The three resistors R1, R2, and R3 in the left circuit are connected in parallel. They're connected to the same two terminals A and D and have the same voltage V1 across all of them. On the circuit on the right, we have a single resistor REQ, which is connected between terminals A and D. What we are interested in is a relationship between the resistors R1, R2, and R3 and the resistor REQ in the right-hand side circuit. The current through the three resistors in the left-hand side will be shown as IR1, IR2, and IR3. For the resistor REQ, the current through it will be I1 as shown. Consider the circuit on the left and we write a KCL at node A, and we will have current entering will be I1, and this must be equal to the current leaving node A, which is IR1 plus IR2 plus IR3. From the right-hand side circuit, we can write that I1 is equal to V1 over REQ, and similarly for the other currents, we can write IR1 is V1 over R1, and so on. We can cancel V1 from both sides of this equation, and we will be left with 1 over REQ is equal to the sum of the reciprocal of the resistance values on the right-hand side. In general, if we have n resistors in parallel, then the reciprocal of the equivalent resistance will be equal to the sum of the reciprocal of the resistor values on the other side. Also recall that the reciprocal of resistance is called conductance, and if we write GEQ is equal to 1 over REQ, then this is equal to G1 plus G2 and so on, where GI is equal to 1 over Ri, where I has a value between 1, 2 till n. Of particular interest is the situation when you have two resistors in parallel, such that 1 over REQ is equal to 1 over R1. This can be simplified by having a common denominator, and the numerator will be R1 plus R2. Simplifying it for another step, we will get REQ is equal to the product of the two resistors divided by the sum of the two resistors. This formula of the equivalent resistance of two resistors in parallel will be useful and will be used often in circuit analysis. We consider the case of current sources in parallel. The circuit on the left has 3 current sources, and the circuit on the right has 1 current source, and we are interested in finding the value of the equivalent current source JEQ, which will give us the same behavior as the circuit on left. To get the same behavior from both circuits, we must have the current JEQ also equal to the current on the left-hand side circuit as shown. If we write KCL at node A on the circuit on the left, we have the currents leaving as JEQ and J2, and this must be equal to the currents entering node A, which is J1 plus J3. Or JEQ must be equal to J1 minus J2 plus J3. Therefore, when you have current sources in parallel, you add up the values of the current sources carefully with the appropriate sign and get an equivalent current source, which will represent the summation of all these current sources together. Finally, we look at the situation of voltage sources in parallel. We show two voltage sources, E1 and E2, in parallel. They're both connected to nodes A and B. If we write a KVL for the simple loop ABA, we will get that a voltage rise of E1 minus a voltage drop of E2 must be equal to 0, or E1 must be equal to E2. What this tells us is that if you connect two voltage sources in parallel, then they must have the same value, otherwise KVL will not be satisfied. It also tells us that we cannot connect two voltage sources of different values in parallel.